So now what I'm going to do is summarize 20 years of work before the break, or maybe between now and the break. The work I'm going to summarize, I'm going to do it in a very simple / simplistic ways, meaning I will ignore some details, but still. The work I'm going to talk about has only to do with registers. I'm only going to focus on registers, this famous read-write object. It turns out that this object looks simple, but actually it is not. And when understanding register algorithms, there are a lot of techniques you will actually be able to reuse for other kind of objects. Remember, the register is this simple object that, when used sequentially, returns the last value written. This is what I know about the register. For the sake of this, it contains only integers. I assume that the initial value of the register, when it is created, it contains value 0. Okay? Okay, good. Now, the game is the following. We want to build registers that are atomic and weight-free. This is what we want. But we're going to assume that we don't have that. The machines, actually, that's true. If you buy a machine now from IBM or whatever, it will give you some sort of registers, but these registers are not atomic and weight-free. It gives you shared memory, and the shared memory is composed of cells. Each cell can be viewed as a register, but this register is not atomic. Okay? It has a weaker semantics. It doesn't guarantee that every operation appears to execute at some point in time. In fact, a long time ago, Leslie Lamport, have you heard the name Leslie Lamport? Good. Defined a space of registers. So he tried to imagine, he looked at the hardware, he tried to imagine what semantics a register could have. And he came up with an interesting definition, and his definition can be broken into 3 dimensions. The first question he asks is, what does the register contain? And he defined 2 categories. Either it contains only Boolean values, 0 or 1s, or it contains several values, not only 0 and 1s. In our case, given that our register contains only integers, multi-valued means it contains 0, 1, 2, 3, 4, and up to some point. Okay? This is the first classification, and you are going to see that this classification makes a difference when you build concurrent algorithms. Now, dimension 2 is the following. And again, you have to go back some time ago and then realize, how did he come up with this classification? Because as you will see, this classification is extremely important when you build concurrent and distributed algorithms. The second dimension is how many processes are allowed to read or write in the register. And he defined 3 categories. The first category, whenever you create a register, okay, in its constructor class, you say this register is going to be read by P1 and written by P2. Over. Nobody else is able to read, nobody else is able to write. Okay? We call it single reader, single writer register. Of course, if P1 equals P2, this is a local register. I write in it, I read in it. It's not interesting. So the first interesting register is one that is shared by only 2 processes, the reader and writer. Okay? Notice that this models a one-to-one communication exchange between 2 machines, if you want. Okay? The second, slightly more sophisticated register enables multiple readers. You have n processes that can read and 1 that can write. And the third category, which is what you ultimately want in a large general purpose program, is a register that can be read by multiple processes, written by multiple processes. Okay? Now, this dimension 1, what does the register contain? Dimension 2, how many processes are allowed to read and write? Dimension 3, how does the register behave when it is accessed concurrently. The Holy Grail is atomic. This is what we want. This is the Holy Grail. But reality is not always like that. There are two categories that are weaker than atomic or linearizable. A safe register is considered the weakest from the behavior perspective. A safe register is a register that guarantees only the following property. The property is, if it is accessed sequentially, meaning all operations execute one after the other, which might not happen in practice, but if it happens, the read returns the last value written. Okay? So what we are saying here is that a safe register is a register that, if by chance it is accessed sequentially, it behaves as expected. But if it is not accessed sequentially, meaning if an operation happens concurrently, remember that sequentially means no two operations overlap. An operation starts when the other one has already terminated. This operation is concurrent. In this case, all bets are open. What does it mean, all bets are open? It means a concurrent operation can return anything, of course, anything in the value domain of the register. So for example, if the register can contain any integer, this read could return 25. Nobody has ever written 25, but this read could return 25. It doesn't mean that it will. It could. A safe register doesn't guarantee anything when an operation is concurrent with other operations. Okay? So this is considered weak semantics. So this one here always returns okay. There is no choice. The right always returns okay. Yeah, this read here comes after the other operation. So it has to return the last value written, this one. But this one is not sequential. The intermediate semantics between safe and atomic is what is called regular. The regular says, again, it is a safe register. If accessed sequentially, read returns the last value written. But if there is a concurrent operation, things are slightly, I would say, subtle here. A concurrent read returns either the last value written or the value concurrently written. So the last initial value, remember, we assume is 0, which means that this read that is concurrent, as well as this read that is concurrent, each of them have a choice. Either they return the last value written, 0, or the value concurrently written. For example, this one could return 1, and then this one returns 0. Or this one could return 0, this one could return 1. Or both could return 0, or both could return 1. Is it clear what I'm saying? By the way, remember, I told you this register abstraction represents a file. In fact, it represents the abstraction of what is called today storage systems. You have full conferences on storage systems. Okay, they build the abstraction of a register, they implement it in cloud, they implement it in this and that. At the end of the day, they have to agree on what the semantics of their storage system is. And they use, usually, these definitions. They say the storage system is safe, or regular, or atomic. These are back to these concepts defined by Lamport in this abstract way. I'm simply saying that these notions apply today in the practical world. And of course, by the way, is this atomic? Obviously not. So regular and atomic differ. They differ because atomic tells you, remember that if you think about the atomic semantics or linearizable, you can say, yeah, but linearizable also, forget about this one. Let's forget about this one. If I forget about this one, will this be an atomic execution? What if this guy returns 0? Will it be atomic? Exactly. What makes it non-atomic is the fact there are these two reads. This is what makes it non-atomic. And more specifically, because this one returns 1 and this one returns 0. The difference between regular and atomic is very subtle, but it has big consequences. The subtlety is, if there are at least 2 read operations concurrent with a write, a regular register enables what is called read-write inversion. The first read returns a new value, the second read returns the old value. With atomic, this is impossible, okay? So this is a difference. As you will see, these small differences have big impact. Okay, good. So let me go back here. So Lamport defined in, even 30 years ago, no, 40 years ago, 76, 40 years ago, these spaces of registers, these categories. And at that time, 40 years ago, he raised the question, if a hardware gives me registers, a lot of them, no, tons of them, registers that are Boolean, single reader, single writers, and safe, meaning a hardware that is relatively weak with respect to registers, can I emulate in software, can I write algorithms that use those registers to mimic, to emulate, to build the abstraction of atomic, multi-valued, multi-reader, multi-writer registers? So he asked this question 40 years ago. Do you understand the question? You are given registers in hardware, and you want to give the programmer an abstraction that is much stronger. Because you say, oh, if I give the programmer this weak save register, it's going to be a nightmare for the programmer. The entire job of computer scientists is to hide the difficulty of hardware or network. Lamport asked the question for registers. So the question is, if you are given safe, binary, single reader, single writer registers, can you build on top of them, can you build algorithms, software, that will guarantee to you or provide you with the abstraction of atomic, multi-reader, multi-writer, multi-value? What do you think the answer is? Who says no? Who says yes? Okay, so they outnumber you, so they're right. So the answer actually is yes, but this was not clear 40 years ago. You can build a multi-valued, multi-reader, multi-writer atomic register with binary, single writer, safe register. Of course, you don't build it with one. Think of these as if you are given a class. Once you have a class, you can create many instances of it. Okay? If you have this class, you can build this class. When I say you can build, here I mean weight-free. My game is weight-free. I'm only talking about weight-free. You can, sometimes we say weight-free implement. But for the sake of this talk, I won't repeat weight-free. And this, again, this was not clear 40 years ago. It even came as a surprise, because safe is very weak. Only written by one, read by one. Only contains binary. How can you, with these guys, even if you put a lot of them, how can you build this really abstraction of, if you think about it, a register that is atomic, multi-reader, multi-writer, can contain any value, is like a variable in a concurrent program where you can put whatever you want without worrying about concurrency. Okay, this is a register. It's a variable, you can assign to it whatever you want, read from it whatever you want, and you don't need to worry. It's atomic, it's weight-free. So it's a very powerful theorem. So this is the first theorem I'm going to prove in this morning. I'm going to prove two theorems. This is the first one. The second theorem is called FLP. We'll come back to it later. Okay. Let's start. So the way we are going to do this is the proof of this theorem is, I believe, interesting in its own right. Why? Because I'm going to start from very simple registers and show you how you go gradually to bigger ones. Bigger means stronger ones, improving in some of the dimensions. And this journey is important because the techniques that are used to build stronger registers are actually techniques you find in all kinds of concurrent algorithms. You find them in message passing, you find them in all kinds of things. Of course, they appear slightly differently, but at the heart, they are the same, okay? So before we start the journey, I assume the following, and this is just a terminology. I'm going to give you algorithms, and as Danny did and as Nir did, when we give you algorithms in concurrent and distributed computing, we give you the algorithm of one process, and this algorithm is supposed to be executed by all, okay? Of course, if you want to say only P1 does this, you write if I equals 1, do this. Number I is usually the identity of the process, okay? The process executing the code is implicitly assumed to be Pi. We assume n processes, and remember, I assume that they know each other. Okay, the video game thing doesn't fall into this category, the video ranting. Also, the goal is implement high-level registers, either atomic or regular or multi-reader, using low-level ones. Low-level one means in one of the dimensions they are weaker. So what we are doing is called sometimes transformations. It's like taking a class which has operation OP and building another class which also has operation OP. But this operation OP is stronger. So think of it as some form of overriding or something like that. Here, the base registers have operation read and write. The stronger registers are also operation read and write. But they're not the same, because this read and write is going to be stronger. Okay? So the convention is the operations to be implemented are denoted big read and big write. This is what I want to write, to implement. And the base registers are small read and small write. And I'm going sometimes to omit the return. Okay, good, let's start now. Now, I want you to think. Try to come up with the algorithm yourself. And the algorithms are very simple. Very, very simple. There is this, I think it's even Lamport who says, if you repeat to people that something is simple, they eventually understand it. Because you feel the pressure. Oh, he says simple. Then it must be simple. And then you start, oh, then I should be able to. And then you start thinking about it, and then you understand. This is very simple. Okay, let's start. The first transformation, and we call them transformation because we implement registers from registers. The first transformation is assume you are given registers that are single reader, single writer. They are safe. And you want to implement one register. When I say implement one register, it means implement the big read and the big write operation. Read with capital, write with capital. Multi-reader, single writer safe. This is what we want. How are you going to do it? I give you, think about it, 2 minutes. So the student from the Technion, did you get this already? No. But you can still think. So you have it already. Okay, but I give the others. I mean, you all should be able to come up with this. Michel, you have it? No? So Michel wrote a book about this. But you never know, maybe he forgot. Okay, so who has it? Yes? What's the idea? Yes? Exactly. So if we have n readers, how many single reader, single writer? We need n. We have an array, very easy. In fact, this is trivial. The goal is to get you acquainted with the notation. So the idea is to say, remember that I can use as many of these as I want. I have a class. I can just create instances. So what I say is I'm going to use an array of single reader, single writer registers. The size of the array is the number of readers I want. Okay? When I want to write value v, when I say when, I have a single writer in both cases. When the writer writes, it goes from 1 to n, it writes v, the value. When I read, what do? IMPI, I go directly to register number I return my value. Okay. Is this clear? This is the very first and simplest transformation. If I lose you here, it's going to be difficult later. So I should not be losing you here. If it's not clear, raise your hand. It's not your fault, it's my fault. Anybody find this unclear or something confusing, ambiguous? Yes? Exactly. Yeah, so, exactly. So, my transformation here starts from safe and builds safe. Safe says, the semantics of safe says, if by chance a read comes after write, read returns the previous write, okay? If the read comes together with the write, no guarantees, okay? Now I have 7 readers, but when we say no concurrency, we mean no concurrency between the read and the write. If there are 2 reads, both of them come after the write, they both have to return the value written. The concurrency that is harmful is between the read and the write. Between the 2 reads, this is fine, okay? Yes? No, good question. I'll come back to it in half a second, or maybe in a minute. Yes, I'll come back. They cannot, because these registers that I'm using are assumed. Think of them as if in the hardware, they're only plugged to 2 registers. One write, one read. You cannot have more than 1 to read. Think of it that way, okay? So back to the question. This transformation assumes binary and builds a binary. Can I use this transformation to go from multivalued to multivalued? Will it work? Yes? It doesn't make a difference. Whether I store zeros and ones or more, it doesn't make a difference. Will this transformation work if I had regular regular binary, and I want to build regular? Will it work? Who says no? Raise your hand. Why not? Speak higher. 1. Things start becoming, if we ask these questions, will it work for regular? Then, what about atomic? Would it work? Okay. So now you start seeing that the area is slippery, okay? It looks simple. As soon as you start adding something, it becomes, these questions we are asking are part of some exercise, right? Where are the exercises? When? Oh, okay. Yeah, so please, the best way to understand this, and believe me, even if you think, oh, nobody used these registers today. No, but the techniques we are using, you find them everywhere. So try to do these exercises. The question, does it work for regular? Does it work for atomic? Try to think about it. They are online, but don't think about that online now. After, think about them, okay? Now let's stay with safe. Everybody understand this? I take this for granted. Une fois, 2 fois, 3 fois. Adjugé. Granted. Now let's go slightly more. Now assume I have the safe. I was able to build the multi-reader single writer. Now I want to make it regular. Notice one thing. Now it is as if my hardware gives me multi-reader single writer. Of course, the hardware doesn't give me this. Maybe it gives me say the safe single reader, single writer, but I don't care. I have an algorithm that is already able to give me the abstraction of multi-reader, single writer. So now I can assume it as if it was in hardware. It is weight-free. It's given. Okay? Now assume I have that. It is safe. I want to build regular with it. One safe to one regular. Binary. How do I do that? 2 minutes. So you have it? Okay. Who has it? Who has the idea? Very, very simple. So the first way you should, the first question you ask yourself is, I want to transform this into this. What's the difference between them? The result of the read in the concurrent case, okay? But the difference in the read, but wait. This is binary. It contains only zeros and ones. So what can that difference be, really? The difference can be if there is a write and there is a read, and this write is writing, let's say, 1, initial value is 0, the read comes, what could the read return? If the read is concurrent with the write, it can only return 0 or 1, right? Because that's the scope. So it doesn't look very different if it's just binary. The safe and regular doesn't look really different, except in one situation. Can you see it? Once you see when they are different, you get the algorithm. So when can they be different? In what situation? Yes? If you write the same value, assume the initial value is 0. I don't know the initial value is 0. I want to write 0. I come, I write 0. The reader reads exactly at that time. What can the reader return if it is safe? It could return 1 and 0. If it is regular, it cannot return 1, because regular says you return the current value or the previous value. Are we together? That's the only difference. Now, what algorithm could prevent the reader from returning again 0? Sorry, from returning 1 if the writer is returning 0. I need to find an algorithm that prevents this case. And yes, I'm going to give you. Remember, the algorithm means something in the implementation of the read or the write, whatever I want. Yes? A write performs the read, and so okay, so the suggestion is the writer should be prevented from writing the same value. It's useless to write the same value. So what the suggestion is, the writer reads first, and if he wants to write the same value, he doesn't write it. Okay? But does he need to read the writer? Or can he? He cannot, because there is only one single reader, one single writer. And the process has a fixed role. Either it is reader or writer. If my role is to write, I'm not allowed to read. So what do I do? You see what I'm saying? What can I do? It's even simpler than that. You get the idea, but it's much simpler. There is one reader, one writer. Only one reader, one writer. And let me correct. We assume that everybody knows the initial value is 0. Yes? Exactly. So you know, as a writer, you know what you have written already. You know it. You don't need to read. So the algorithm is the following. Very simple. When I read, I just go directly. This means I don't transform the read. I don't do anything. The read is just direct. The big read is the same as the small read. The write is slightly different. I have a local variable. I call it old. Old means I remember the previous value I written. If old is different than the value v I'm writing, then I write. Because I know that I want to change the value. If the read comes concurrently, I don't care. The read can return the old or the current value. If the old value is the same, I don't write. Is it clear, the algorithm? Again, very simple. Yes? Speak higher. Did I say multiple reader, single writer? Yeah, I forgot I said that. You're right. But you don't even need to read. You're right, and you're right. I forgot that it was multiple reader. So I could do that too. But notice that I don't need to, because I am the single writer. I don't need to go see what's in the register. I know it already. Okay? Good point. So the assumption here is that every process has some local variables. These are not shared. Okay? The first transformation, we go from one register to an array. Very simple. Very simple if we have safe or regular. When we get atomic, things start becoming complicated. Hopefully you will see that when you think about this. Transformation from safe to regular is simple. It's simple. Why? Because I have a single writer and I'm relying on something else here. What is it? What? Exactly. I'm relying on the fact that it's binary. If I could store in the register 3 values, 0, 1, 2, will this algorithm work? Obviously not. So notice again the subtlety of these things. This looks very simple. It looks very simple because I have a full package of assumptions. If you increase the assumptions, you decrease the size of the algorithm. Okay, that's how it works. So here it's very simple because I have a lot of assumptions. Everybody agrees with this? Clear? Good. Now let's be more ambitious. Now we want to store several values. Of course, in applications, you don't want programmers to only write with zeros and ones. Remember, our job is to simplify their lives. So now, we were able to build multi-reader, single writer, regular binary. We just learned how to do it. Assume we have that. Assume now it's in hardware, weight-free. Everything is weight-free here. Now, we want to store several values. So assume I want to store values from 0 to, from let's say 1, to simplify, to 8. The values I want to store is from 1 to 8. Again, I can use several multi-reader, single writer, binary registers. How should I do that? Think about it. What? Okay, how is that called? So the suggestion here is to encode. How would you encode, let's say, let's take a concrete example. Let's say you want to store value 4. What would you do? Say that higher. I use 4 registers. And how do I do that? What do I write in the registers to write value 4? So I have 4 registers. What do I write in them? All of them ones. Why not? Okay, this is one suggestion. The second suggestion is to use 2 arrays. One where I write the value, and one where I say that there is a new value. Okay, so the idea is I have 2 arrays. One of them contains the old value, one of them contains the new value, and one bit tells me where to look. Any other suggestion? None of these work. But very good suggestion. Excellent. Yes? No. We just have binary binary multi-reader single writer, and we want to build multi-valued from 0 to 8, yes? One register, you want to use it as what? A lock. Yeah. So this is a little bit similar to the idea of one register as a, okay, this is a third suggestion, which is a little bit like the other one. Unfortunately, it doesn't work. But any other idea? An idea that works. Will save time. Yes? Speak higher. Have you seen this solution already, or you just came up with it? You remembered. So you have seen it already. Okay, good. So, okay, there are two kinds of solutions here. There are three kinds of solutions. There are the kinds of solutions which consist in saying we are going to use one bit to say this is the new value, this is the old value, roughly speaking. This bit looks like a lock. Anything that looks like a lock doesn't work with weight-free. Never. Okay, by experience, but it doesn't work. Whenever you have this idea that I'm going to use one bit to say the value is new, the value is old, or to, this means that you are implementing locking. It's not going to work. Okay, we can go in details during the break, but it doesn't work. The solution that comes to mind usually is what is called binary encoding. You know binary encoding? How do you code? How do you encode 4 with binary encoding? You say 100. This idea comes to mind also because you say, okay, maybe I have binary registers. In order to encode 4, I will say 100. Unfortunately, it doesn't work. Anybody has an intuition why it doesn't work? Binary encoding doesn't work. Yeah, exactly. So the reason why binary encoding doesn't work is simple, and this is something very fundamental. It comes in all kinds of concurrent data structure implementation. It's because, remember, we don't have locks. Therefore, we should always be prepared to the situation where the read is concurrent with the write. Okay? So assume somebody is writing this value, and the reader comes, and the initial value, let's say, before this, there was 110. Okay, this was the previous value. And the writer wants to write 100. So the writer has to come and say, put this to, the initial value was 010, and the new value has to be 100. The writer has to go from here to here. Okay, so what could the writer do? The writer could say, for example, okay, I'm going first to put this to 0, and then put this to 1. But during this transformation phase or intermediate phase, maybe the reader comes, and the reader maybe finds 000. It returns it. Oh, but this is neither the new value nor the previous value. There is an intermediate state that is dangerous. It's not written. The binary encoding cannot work because it doesn't have an intermediate state that can be okay. You see what I'm saying? Therefore, the only way, not the only, the way that works is called unary encoding. You know what unary encoding is? It's not very effective. How would you write 4? What do you do to write 4? You do 4 registers, and you only write 4 here. If you want to write 5, you put 5 registers, you only put 5 here. 1 here. And the way you get it read and write is what he suggested. So let's see, before the break. So here we are going to use an array of multi-reader single writer registers. of size m. M is the m of the multivalued. If I want to write up to 8, m equals 8. So what do I do? If I want to write a value v, I go to the register v. So if I want to write 4, I go to register number 4, the 4th register. I write 1 in it. Okay? So if I want to write value 5, I go here, I write 1. The value before was 4. Now I want to write 5. I go here, I write 1. And then I go down and I put everything to 0. Okay, this is the algorithm. You go to register number V, you write 1, you go down, you clean, you write zeros everywhere. Okay? When you read, you start from here and you go looking for a 1. As soon as you find the 1, you are happy. You return the rank you found. This is the algorithm. Now, let's look at what I just said here. The initial value was 4, the new value is 5. Assume the read comes concurrently with the write. If the read comes after the write, you agree with me that it's okay. He will find value 5. If he comes concurrently, what can the reader find? The only thing the reader can find is either it will find this 1 or it will not find it. If it finds it, that's fine. It returns value 4. Value 4 is fine. It's the previous value. Or it returns value 5, it's the new value. It cannot return anything bad. You see what I'm saying? This is important to understand. Okay? We have this invariant that, and this is a general invariant in concurrency. No matter where the reader comes, it finds something okay. Okay means previous value or new value. And this guarantee we have with this unary encoding. The idea is not fundamentally or incredibly sophisticated, but again, there are these subtleties. We cannot use binary because it doesn't guarantee this invariant, and the reader and the writer don't go in the same direction. Okay, you can ask yourself, what if they go in the same direction? What could happen? Assume I have a simpler algorithm and I have the writer. Assume the writer first puts zeros everywhere and then puts the 1. Assume I change the algorithm and I make it such that I start from here, I put zeros everywhere and then the 1. What could happen? Raise your hand so that I can see where you are, okay? Yeah, it could happen that if the writer puts zeros everywhere, and for example, the value was 5, and now it writes a new value. So it could put zeros everywhere and didn't have the time to write the 1. Yet, the reader comes. The reader sees zeros everywhere. This is not a valid response. You see what I'm saying? That's why we make sure the writer first writes a 1 and then writes 0. Yes? Yes, we could do that. Yes, yes. You could jump. Fine. It looks maybe easier. Yes. Yes, that's true. What else could it do? Oh, why? Oh, as soon as you write 1 first, that's fine. What is important is write 1 first. That is not. No. Yeah, so the suggestion here is, what if the reader finds zeros everywhere? It can say, oh, this is not valid, I try again. Okay? What could happen if the reader tries again? Looping forever. Whenever you see try again, you say, ooh, this looks weird. Because if you try again once, you can try again twice. If you try again twice, you can try again 3 times, etc. Okay? By the way, I'm not saying this is the only algorithm, but the best way to understand this field is to ask yourself, can I change this? Can I change this? Will it work? So I'm giving you a couple of cases in the exercises. Try to do them. These are what I believe to be subtle cases. But as you will see, you change one thing, sometimes it works, you optimize. But many times it doesn't work. Okay? So I suggest to stop here, and then after the break I will finish this theorem, and I will move to another one that I believe is fundamental.